Hey guys, welcome back. Well, I thought I'd put together a little video with some thoughts on adding HA to the red or the luminance data for some of the galaxy processing that I've been doing of late. Now, there's a formula that is around, it's well known, it's probably being used by most, perhaps yourself, in doing this process of adding the HA to the red data. I just want to take a new look at that formula and point out a few things where maybe we can simplify the process and to help us understand a little bit more about what it's doing and how we can go about trying to add in HA data, as we can see here in M33, to an M33 image that has no HA data. And that's what we're going to talk about. All right, the process is a two-step process of combining narrowband and broadband data. And the first time I heard of this was back in my early days of trying to learn PixInsight for the first time. I used to watch some videos by Harry Page from Harry's Astro Shed, and he referred to a procedure he got from Vincent Perez from the PixInsight development team. And I think that's probably the first source that I've ever seen of this, but it's been around and it gets reiterated, as it will again here in this video. But the whole idea is to first create a version of the HA data that you have that is just the HA part that you want to add to the red filter. So in other words, we're trying to extract out all the stuff that's already in the red filter, and we just want the stuff left over that's unique to the HA data. We take that new HA signal, subtract the noise from it, magnify it up to a level that we think is appropriate, and then add that to the red signal to get a combined HA and red signal to be added in with the green and the blue, so that we can get a combined color image that has the HA built into it. Now, this procedure is general. You can use it to add oxygen 3 to the green or the blue filter, or you can use it to add the HA to the luminance filter. And in this case, I'm going to be using three examples, three galaxies that I've done some imaging on with three different telescopes, just to show how some of the parameters can vary depending on the type of image that we're talking about and its source. Now, the first thing we need to take a look at is the filter transmission characteristics. It's not going to be ultimately important, but it's a critical player in the form of the formula that you're probably familiar with. For me, I'm using the CWO broadband and narrowband filters, and if we focus on the red and the HA, you can see that the red filter has about 100 to 110 nanometer bandwidth at the full width at half maximum. In the HA zone, we have about 7 nanometers at full width at half maximum, and of course the HA line is about here. So in essence, the HA data, the HA filter, is recording about 7% of what the full band broadband red filter is seeing, and that's kind of important. In the first step of this two-step process of adding HA to the red data, the first thing we have to do is implement this formula in pixel math within PixInsight. Now, you've probably got this if you've been doing this procedure. You've got a formula that probably looks a lot like this. And basically what it is, it's the bandwidth of the red filter, the broadband red filter, divided by the bandwidth of the red filter minus the bandwidth of the hydrogen alpha filter times the hydrogen alpha image minus the red image times the bandwidth of the hydrogen alpha filter divided by this difference again between the broadband bandwidth and the narrowband bandwidth. Now, if we put in the numbers, that looks like 100 divided by 93, so this is a number that's slightly larger than 1, and over here you get a 7 divided by 93, so it's a very small number that we're multiplying times the red filter. Now, here's the thing. This formula looks kind of inscrutable. It's difficult to tell what's going on, but if we can rewrite this into a mathematically equivalent form, we would have a formula that looks like this. And now things become very clear and very logical as to what we're trying to do. So this first term in the bracket is the HA image minus a portion of the red image. Now remember, the red image covers the bandwidth of the HA filter, right? So it's only 7%. So if we take 7 nanometers divided by 100 nanometers, that's 7%. That means that if we're just taking the portion of the red light that's in the HA bandwidth and subtracting it from the HA image. In effect, we're taking that portion of the red image that we recorded with our broadband filter that's in the bandwidth of the HA image and just subtracting it from it. And hopefully, if we were lucky, it would take the stars, it would take the core of the galaxy, and we'd just be left with the little bits of the nebula and the distant galaxies that are in the spiral arms. Now, it doesn't always turn out that way for reasons that we'll discuss here in just a second. But that's the idea, and that's a very logical thing to do. This term over here is just a scale factor that's slightly larger than 1. We're taking out, for example, about 7% of the light from this image, and so what we're doing over here is multiplying by a number that's about 1.07. So it's trying to maintain an equivalence of the intensity of the signal in this new updated HA data that it had before. But here's the problem, and here's why whenever we apply this formula, we continually have to play with the NR number here to make it do what we want it to do. The term in the brackets assumes that the hydrogen alpha and the red data were acquired with the same imaging parameters. In other words, the same gain, the same exposure, the same part of the sky, and so on. And that's not really the case. At least it isn't for me. I tend to use a larger gain for HA. I tend to use a longer exposure for HA. So, for example, what I should be doing to fully compensate for that effect, I should take this number, call it 0.07 here, and multiply it times the ratio of the gains for relative to what I use for narrowband versus broadband, which is going to be a number around between 2 and 3. So we're already up to now around 0.2, this number, instead of 0.07. The next thing that I tend to do is I take a 300-second exposure in HA, for example, but a 100-second or 200-second exposure in red, depending on which telescope I'm using. So there's another almost 1.5, say, that you can multiply this expression by to amplify the red up to the level where HA is so that this subtraction makes sense. And so now we're talking about a number in here that's, say, 0.3 as opposed to 0.07. And that's why when you're using this formula in this form of the equation here, you find that you have to lower this number, the NR, the bandwidth of the red filter. You have to lower it in order to get the effect you're looking for. Notice that if you lower decrease the number of the red filter here, you're actually making this number bigger so that you're taking more signal out of the HA data. In the second step, we take that image and then subtract off the median of that file. Now, the median is basically the pedestal, the noise floor. So we're essentially taking the modified hydrogen alpha image with its noise floor and now subtracting off the noise floor so that all we're adding is the hydrogen alpha signal that we want to add to the red channel, but we're also multiplying it by a factor over here in order to amplify it so that when we add it to the red, we get an image where we can actually see probably an amplified version of the hydrogen alpha that would actually be there. We just adjust the scale factor until we get the desired level of HA contribution. It's an arbitrary constant. There's no formal guidance on what this number should be. Just look at the image and see if you like what you're seeing. Let's consider maybe a more direct, possibly even more honest approach. And we'll take this formula that we rewrote from before and let's just think about what we're doing here. As I said, the fundamental problem here is that the hydrogen alpha and the red data are being acquired with different imaging parameters, which means we come in and play with the NR number in order to make the new hydrogen alpha data look like what we want it to look like. Let's just skip this part where we use these filter bandwidths because we're going to play around with the numbers anyway, and let's just write this as the HA image minus the red image times some factor, say roughly 0.25 as a starting point. And then we can iterate by playing with this parameter, increasing it or decreasing it as we need in order to produce the image that's mostly HA and a little bit of noise left over, and then we'll deal with the noise in the second step. The next thing is we have this amplification factor over here, and it's kind of a pointless amplification factor because we're playing around with the numbers anyway, so why don't we just get rid of it, and then in the next step of this two-step process where we have this arbitrary factor that we're taking and multiplying or scaling up our hydrogen alpha contribution, let's just say, forget this. There's no point in having two arbitrary constants floating around. We'll just leave it out. That's why it's not in this first formula here, and we'll just put it in here, and maybe a good starting point for this S2 parameter is, say, 1.0. But once again, you can go up or down and adjust the numbers until you get the image you want. And I think if we first go and find S1, to get the new hydrogen alpha signal that we're trying to add to the red, and then we play with S2 to get the red signal up to a level where we can actually see our hydrogen alpha contribution. That's what we're after in our ultimate goal, to combine a combined red hydrogen alpha signal with the green and the blue to get a composite image. Let's go over to PixInsight and see how this works on a couple of different galaxies. All right, so here we are in M33. We have the red data here on the left. We have the corresponding hydrogen alpha data on the right. You can see these little knots of hydrogen alpha scattered throughout the arms of M33. These images were taken with my Explore Scientific ED102. Now, the first step is that we want to try to mess around with this hydrogen alpha data to get a version of the hydrogen alpha file that has as little of the red data in it as possible. And so for that, we have a process here in Pixel Math. If we go over to the formula, you can see what I'm doing. I have the original hydrogen alpha file image, which is this one here, and then we're subtracting from it the red file, red filter, which is this image over here, times some constant s. If I go over to the symbols area of this, I'm starting with a value of s equal to 0.25. So let's just go ahead and run this. Now, by the way, I've also I'm creating a new image, and it's going to be a grayscale image. So I'm just going to press this button. It's going to create a new image. I'm going to look at it and see if I like what I'm seeing, and then make adjustments to S until I do like what I'm seeing. So if I just execute this as it is, here's the image I come up with. We're still in the linear world, so I'll do a screen transfer, and we get this kind of a result. Now, if I look at this, and I back out from here to see what the original file looked like, full image looks like, it doesn't look that different. So it doesn't look like we've had that big of an effect, though it has had some. We're starting to get rid of some of the noise around here and to isolate some of that hydrogen alpha, but it's still not quite good enough, I don't think. So now I'm going to go back into S, and I'm going to change it to 0.3. In other words, I want to increase the amount of red that I'm subtracting from the hydrogen alpha data. And we'll just run it again. And now I've done too much, right? I've got no noise left. Certainly the hydrogen alpha is there, but one wonders, given that I've been so brutal on the background noise, I may have lost some small signal contributions to the HA that I might want to keep. Now remember, in the next phase, we're going to subtract off the median level from this image, so it's okay to have a little bit of noise left over that we can subtract off later. But for now, I want to try to retain as much of that hydrogen alpha that may be there, so that I can include that in the red image. So this is a little too brutal. I'm going to come down and call this about 0.27, say. And if I do something like this, now it's getting down to a level where we might want to do some work. We still got some noise in the background. Again, we're going to be subtracting off the median from this, so that's okay. There'll be still a little bit of noise left over, but we're going to deal with most of that noise. We're getting all of the hydrogen alpha that we want. A lot of interesting hydrogen alpha contributions in M33, so we're getting all of that. Unfortunately, we're still getting some of the stars out here, but we have cut down on their contribution, so hopefully when we add this back to the red channel, we're not going to make those stars too red. But yes, we are unable to fully get rid of or eliminate the stars in this modified hydrogen alpha file, and I think I might have iterated one more time and gone to a 0.28 to bring this noise level down a little bit more, but it kind of looks like this. And in fact, my modified HA, or my new HA file, looks like this with a parameter, I think, of 0.28 is what I came up with. And so this is the modified, or the new hydrogen alpha data that we will now use in our second step of our process, where we have the red channel, the red data, which is this file here, plus, and you'll notice the parentheses we have here, we have the new hydrogen alpha data that we have, so that's that new file we just created from the first step, minus the median, this formula here. This is a function that you can use within the pixel math process here. So this calculates the median of the image, of the new hydrogen alpha image. So we're subtracting that noise off, and then we're multiplying that by a new factor S, which is over here in the symbols, and I'm starting off with a factor of 1. And again, within the destination, I'm creating a new image, a new grayscale image. And if I just run this, it will give me now what is now a combined red and HA file. And you can see that we have in here some of the hydrogen alpha that we had in our new hydrogen alpha file. We just added it in. It doesn't look like it's done any real damage to our red data, so we're not affecting the balance of the red data too much. And if you wanted to play with this more, you could say, well, maybe that's not enough for you, so you might want to try a value, say, of 2 to boost up the contribution of the HA to the red channel. And I could implement that, and we would have even more obvious contribution, though it doesn't look dramatically different. The HA contribution is boosted a bit more in this image than it was in the last one. Now, when we get done with all of that and we combine the now modified or the new red channel with the HA, this is what we get. Whereas if we did not include the HA in with the red channel, we would have just a more of a bluish color and no real indication of all that hydrogen alpha that's scattered throughout the signal here. Now let's go take a look at a couple of other images just quickly. We won't go through the steps, but for example, we have the Andromeda galaxy. This is a picture. These are pictures taken with my Williams Optics GT81. Over here we have the red, and over here we have the HA. In this case, the HA tends to group around the perimeter of the galaxy, around these spiral arms here. And so we just want to add that into our data. And in fact, when we go through the first step of finding the scale factor, this is an unusual case that actually works very well. You'll notice that when we subtract out the red with the appropriate scale factor, we are eliminating the core, so that's good, and we've eliminated, look at all these stars that are eliminated. We don't see any HA contributions from these stars. All these stars that we see around here are all from the red filter, basically, that we can take out, and so they don't even contribute at all, but we do have the remaining little knots of hydrogen alpha going around the perimeter of the galaxy. Now, if we didn't include the hydrogen alpha, we would see something that might look like this. And by the way, these aren't processed color images. This is just the product of the channel combination with and without the red channel with the hydrogen alpha and the red channel without the hydrogen alpha, which is what this is. This would be the first step of going in and starting the processing to work on the colors, and then I would bring in the luminance data to punch up the detail in these plots. But this is just the first, the starting point, and you certainly don't want to go too far beyond this, because if your hydrogen alpha isn't showing up here, it's not going to show up later. So here you can see that the hydrogen alpha is showing up as all of these little red dots and red regions going around the perimeter of the galaxy, and there's quite a few of them around the edge here, and so that's why you kind of want to bring these in using this combination technique. And of course they're not there in any level of visibility if you don't go to the trouble of bringing in the hydrogen alpha. Let's go look at one more example. Now over here we have M51, the red channel, and M51 with hydrogen alpha. And you'll notice in the red channel the arms are fairly bland looking and don't show any of the contributions that the HA is providing over here. Here there are many contributions of HA in the spiral arm of M51. And when I go through that without including the hydrogen alpha, this is what I get as a starting point in the color RGB color space. And then when I add in the hydrogen alpha, we get to see all of these very colorful knots along the way around these spiral arms. So it adds quite a bit of interest to M51 that it would not otherwise have. All right, so in this example, what you've seen is this iterative application of this two-step process for the 3 different galaxies we looked at, collected with imaged with 3 different telescopes. And the big thing that comes across here is look at the range of variability we have in this, I'll call it arbitrary constant here. There's quite a bit of range in these numbers, so these numbers don't mean anything to you. Don't try to use these numbers, just recognize that there is a good bit of variability with this S1 factor on the red channel that we're pulling out of the hydrogen alpha data in order to come up with the new hydrogen alpha file. Then in the second step of the 2-step process, we're taking the red channel and adding in this new hydrogen alpha we just created, but we subtract out the noise floor from the new file, and then we multiply it by a different number. And now you'll notice there's quite a bit of variability in this scale factor here. Some iteration is certainly going to be required. With pixel math, it's pretty quick to get through this process and have a systematic way of adding in hydrogen alpha so that your images can pop with that contribution to the galaxy images that we're taking. Okay, so this method that we were talking about is kind of a two-step process where we first extract the desired portion from the narrowband image, and then we take that now new version of the narrowband image, scale it up, and add it to the broadband image for our final combined, the red plus the hydrogen alpha. We use different imaging parameters, so the original intent of the formula, which was to simply, for example, take out that proportion of the red filter that contributes to the hydrogen alpha bandwidth, is kind of lost because we're not using the same gain, exposure setting, etc. And so as a result, we lose and have lost the physics-based meaning of what that original formula was all about. So if we're going to throw out the physics-based formula, we might as well just use a simple formula for the first step and say, I'm going to create a new HA file based on taking the HA minus the red times some small scale factor, probably as a good starting point, use S1 equal to 0.25, but don't be afraid to change it. In the second step, we can use pixel math once again to take the newly created hydrogen alpha file. We use the median function here to subtract off the noise floor from that file so that we're not adding more background noise to the red channel, but then we boost up the remaining part, the signal part of the hydrogen alpha, with this factor S2, and it's probably a good idea to start with a value of 1 here, but you can go up or down depending on what your combined image looks like, and don't be afraid to iterate through this several times because at the end of the day, that's your image and your choice. Okay guys, well, I felt obligated to put together a video on combining hydrogen alpha with the red channel. So there you have it, just another take on an accepted procedure that we've probably all been using. But I thought I'd share that with you and see if that helps simplify the process for you. So give it a try, and I'll see you later. Clear skies.